So let's start with a little bit of very basic theory. As I mentioned, a sensor is a device which converts a physical stimulus into something that the data acquisition system can measure. And so the most basic principle here is if we have a material, can be a piece of silicon or a piece of steel, and we put stress on it. We simply take a piece of metal and we squeeze it. That puts stress on the metal, and that metal actually causes strain. Now, just to be clear, there's a difference between stress and strain. Stress is actually putting force onto something. You're stressing it. Strain is the property that material actually changes its dimensions when you put stress on it. Okay, I see somebody nodding over there, right on. That's why we use things like strain gauges that measure the deformation in materials instead of, it's not really a force gauge, it's a strain gauge. Okay? And so we put a stress on there. Like for instance, if we were to compress that material, it gets a little shorter and it gets a little thinner in cross-section. Or fatter in cross-section. Now, if we bond what's called a strain gauge to that piece of material, that strain gauge is comprised of a zigzag pattern of a metal alloy that changes its resistance when its cross-sectional area changes. It's as simple as that. If I make it shorter, the wires get a little fatter and they conduct electricity a little bit better. This principle is key to virtually all the measurements we make. So if we put tension on that thing, it stretches it out a little bit, it gets a little thinner and the resistance goes up. You can see if I put an ohm meter on there, when I compress it, the resistance goes down, and when I lengthen it or put tension on it, the resistance goes up. So why don't we just put an ohm meter on the thing? Well, it turns out that strain gauges change their resistance in very, very minute amounts. So a typical strain gauge would be a 350 ohm equivalent. If you put a lot of stress on there, it might only become 50.1 ohms. Okay? It takes an incredibly good ohm meter to read that. So we don't do it that way. We'll talk about what the right way to do it is. Now, strain gauges can come in all different patterns. So a lot of times we're not just interested in the force in one direction, we're interested in the force in all directions. You know, in this world we talk about the x-axis and the y-axis and the z-axis of the vertical. So you can actually get a strain gauge pattern like this that allows you to, by looking at the output from all three gauges, you get what we call a force vector. So not only can I tell the magnitude of force, I can tell what direction it came from. And that's again a fundamental property in the load measurements we make. We're making measurements of things like the upper and lower neck, F of x and F of y and F of z. Typical load cells have maybe 40 strain gauges in those things to isolate the forces. Now, strain gauges are actually, on a piece of metal, they're actually a very thin flexible substrate with that metal changeable resistor glued onto the piece of metal. So if you look at it in blown up cross section, you can see there's the specimen, which is often the body of the load cell, a glue layer, and then the strain gauge itself. So what do we do with a strain gauge once we have it in our hands? Well, way back in 1843, a guy named Charles Wheatstone, one of the brilliant scientists in England of the day, there were a whole bunch of them that have things like units of measure named after them, like the watt. It ran in the same crowd as Charles Wheatstone. And what they discovered, they had, if you can imagine, we have trouble using an ohm meter today to measure strain. Well, they really had a problem back over 150 years ago. So what Wheatstone figured out was if I take 4 resistors and I assemble them into a diamond-shaped bridge, that what happens is it's like making 2 voltage dividers, where if I apply a voltage between plus and minus excitation, I will get roughly half the voltage at one signal lead and roughly half the voltage at the other signal lead. And so I can put a very sensitive voltmeter between the two, And then if any one of those resistors changes a tiny bit, I can get a much amplified reading, if you want to call it that. And so the Wheatstone Bridge became the cornerstone of making load cells, accelerometers, all sorts of gauging applications, and it remains so to today. We really don't have a better way to do it. So if I fix all of these resistors at a precise 350 ohms, and then I make the strain gauge a 350 ohm gauge, and then I put strain or stress on it, I'll get a reading on the voltmeter, tiny voltage output. That's all nice and it's isolated from the big voltages I have to apply. So graphically, if I hook up this strain gauge into a Wheatstone bridge, which I can also represent like this, let's say that this gauge is resistor number 2 in this bridge. The strain causes the resistance to change and creates a small voltage differential on the bridge. What happens if I compress this specimen? The resistance goes down. R2 pulls the plus signal up toward the plus excitation a little more, and presto changeo, I have output from my transducer. Likewise, if I stretch the transducer, I get tension. Load cells all throughout the dummy, coupling the seat to the seat pan or the aircraft structure, they're all pretty much based on the same principle. We've got a load cell that typically has 4 or 5 precision posts made of steel, and there are strain gauges on all sides of those posts that allow us to differentiate the forces on the load cell acting from one end to the other. So here's a typical load cell, or this is a neck load cell, or maybe a leg load cell. And if I fix one end of the load cell and then put forces over here, the gauges in the middle tell me what's going on with the forces. And we can isolate up to the 6 individual measurements of the 3 forces and the 3 moments. The same principle is used to make accelerometers, albeit in a different way. But what we do is we have an accelerometer that has some kind of mass in here. We call it an inertial mass that can put strain onto some kind of a little electromechanical member that has a strain gauge on there. So an accelerometer is really a mechanical variation of a strain gauge application. We often refer to these as piezo-resistive accelerometers. They're often made out of micro-machined silicon that's got impurities doped into the silicon to make it work like a strain gauge. Often these accelerometers, like the Endevco and MSI accelerometers, are called micro-electromechanical systems. So if you hear the term MEMS, about once a month I have someone email me or call me and say does your system work with MEMS devices? And it's like, absolutely. MEMS is just an acronym for a bridge transducer that's made out of micro-machined silicon. And they come in all different types. So some of the other things we might do in the impact lab are we might use potentiometers, basically something like an old volume control, to measure deflection. And it's a very simple thing. It's a variable resistor. I put a voltage on the top and the bottom, and then I move a little mechanical wiper on the resistor, and it changes the voltage. We use these for things like rib deflections, chest deflections, and maybe even vehicle crush or other parameters where you need a displacement measurement. Notice that even though it doesn't look quite like it, the potentiometer is built into a Wheatstone bridge. Here I've got one half of the Wheatstone bridge, and the potentiometer forms the other half. Now, a different class of sensor is what we call active. Now, these are not bridge transducers, and they do not have a Wheatstone bridge. It's important because if you're setting up a data acquisition system to work with a sensor, you need to know what the fundamental technology of the sensor is. If it's a bridge, okay, they're all pretty much similar. There might be some nuances, you know, like what's the bridge resistance and how much output does it have, but they're all basically the same. With active devices, they typically have some kind of sensing technology inside, as well as a tiny circuit that amplifies the signal. It might regulate the power supply. It might do all sorts of stuff in there that you know nothing about. The bottom line is that an active transducer needs to be treated differently than a passive transducer, which is what we call bridges. And I'll talk about that in a little more detail in a minute. But these things actually put out an output voltage that's very high level, and they have circuits as well as sensors inside. Okay, sensitivity. The most important thing you need to have a good handle on when it comes to setting up a transducer. Sensitivity is the numerical relationship that relates the physical stimulation to the electrical output. That means if I put X number of pounds, newtons, Gs, I get this amount of voltage out of it. That's simply put what it is. It relates the physical input to the electrical output. Sensitivity in transducers can be either what we call proportional or not proportional to excitation. Passive transducers, like all of the Wheatstone bridges, that includes load cells, accelerometers, moment, force and moment gauges, they are all what we call passive. They have no electronics, and their output is proportional to their input voltage, and we call that proportional. So you can see piezo-resistive accelerometers from Endevco, MSI, and N-Tran pretty much are all passive. Dummy load cells are passive. Strain gauges themselves are passive. Active transducers have the electronics we talked about in addition to their sensing elements. Therefore, the output is typically not proportional to their input, and we call that simply not proportional. That is important because the data acquisition systems will always ask you the question to define what kind of transducer you're working with, and you have to know this. Important to note, there truly is no standard for communicating transducer sensitivities in the world. Transducers of different types communicate it differently. Similar transducers from different manufacturers communicate it differently. It's important that you understand how to convert what the manufacturer for a sensor gives you into the numbers that the data acquisition system needs. Because they're all the same. They all need that setup information. Our standard format is for sensitivity is millivolts per volt per engineering unit. We use the term engineering unit as a placeholder so we don't have to keep saying, oh, now was that pounds or Gs or newtons or, you know, or inch pounds. So when we say engineering units, it's whatever you're measuring. So the standard input the DAS needs, and this applies to everybody, is how much output from the transducer do I get for each, say, volt of excitation I supply for how much force or load or Gs. So simply put, I have an excitation source here, I have a sensor, and I have an amplifier. So sensitivity means the millivolts of output from the sensor per volt of excitation applied per the physical stimulus applied. And that's what we have to do. We have to get it into that format. I'm not going to go through all these details. They're in your notes, but I gave just a bunch of examples of passive transducers, and these are real-world examples. If you get an accelerometer, they'll tell you the sensitivity is 0.2 millivolts per G using 10 volts excitation. You figure it out. So you've got to know to divide by the excitation to get a more universal way to communicate it. If you buy a load cell, it might say your output is 1.5 millivolts per volt of excitation at rated capacity. Okay, well, I've got to divide that out and get it back into millivolts per volt per pound, and so on. Now, the same thing holds true for amplified sensors. As we discussed, amplified sensors are generally not proportional to excitation, so that's the first thing you need to do is tell the system that it's not a bridge, and then you need to get sensitivity into what we call the millivolt per engineering unit format. So let's talk about the full-scale range of transducers. In SAE J211, there's something defined as a channel amplitude class. And that's really just defining the upper limit of what you might need to measure in a given test configuration. So let's say I'm running a test and I know that my channel amplitude class needs to be 500 Gs because that's the range I need to be prepared to measure. That's all that means. Now, SAE J211 does talk about what we call resolution, and we're going to go into this in a little bit more detail, but there's a requirement that the data acquisition system and the sensors need to be able to resolve down to 0.2% of the measurement range. They're basically saying if you're using a sensor and a data acquisition system that gives you 2% resolution on the low end, that's just not good enough. So the target is to get down to the smallest measurement you can take is 0.2%. So for example, with a 2000 G accelerometer that's very popular in impact testing, if you have a 16-bit system, I don't expect you to know all the, the nuances of that, but basically 2 to the 16th, the 16-bit DAS, means that you've got 65,000 discrete amplitude steps that you can measure. So a 2000 G accelerometer measures plus and minus 2000. So that means that each step is worth about 0.06 G. When you do the math, the real world resolution is something like 0.01% of full scale. So you don't have to worry about meeting the SAE J211 requirement. Now that used to be more of an issue back in the days when people used 12-bit or even 10-bit or 8-bit A to D. But now pretty much everything is 16-bit, and that's actually one of the big benefits of going that way. So how do you select the full-scale range? Well, all the DAS products out there will say, tell us what your maximum measurement is. Basically, tell us what your channel amplitude class is. And so you put a number in, and there's sometimes a little bit of judgment in how you set that up. But for example, in the automotive crash test world, we typically tell our customers that the best performance they're going to get out of the system is going to be if they set up so that the x-axis accelerations in a frontal impact, that's the greatest, are in the range of 400 Gs. And then the off-axis might be 100 Gs full scale. So there's a little bit of judgment. You're not really in any trouble if you pick a higher level, but it's a decision you have to make. How much do I want to be able to measure before the system runs out of room? I'm sure some of you in the room remember shunt checks, or maybe even use them today. When you wire up a transducer, mostly bridges, Wheatstone bridges, sometimes we switch in a resistor across the bridge, and what that does is it has the effect of simulating an applied load to the transducer by offsetting the bridge just like a real load would do. So it has the benefit that shunt tests can be used to cross-check the setup, and they can be used to tell you, gee, is the sensor plugged in? Is the cable good? Is the transducer likely working okay or not? Today, we use a technique that's called shunt emulation, and it basically does the same thing that old shunt tests used to do, but what it does is it takes the sensitivity of the transducer, it takes your desired full-scale measurement, the excitation voltage, and it actually calculates an exact shunting voltage to apply to the transducer to deflect it something like 100% of full scale. And so this technique is sort of under the hood, but it's now the most common method for simply doing a cross-check on the transducer and the wiring. So what about calibrations of transducers? I think you're going to get a chance to see some cool stuff out in the tour, but the term calibration really means comparing a reference known device to something that needs to be calibrated. And so one of the things that we use all the time is we use equipment that's been calibrated and perhaps certified to be accurate to the National Institute of Standards and Technology. And we do that all the time. Our shop is full of instruments that were calibrated to it and certified that they're accurate. So all that really means, whether it's a sensor or a data acquisition system, is you compare known inputs with the unit you're calibrating, and then you've got some tolerance and uncertainty. These days, you might hear the term ISO 17025. ISO is International Standards Organization. 17025 is it's basically the internationally recognized practice for making measurements for calibration. And so DTS in the last year became certified by the A2LA, which is the American Association of Laboratory Accreditation. Basically, we're accredited that we know how to measure stuff in accordance with the ISO standard. And you're going to hear more about that in the coming years. 10 years ago, nobody really cared much about it. But when you do your calibrations, you're going to start hearing people say, is it ISO accredited? And final word, my boss in 1979 taught me, never set up a system. He said, I don't care that this 5,000-pound load cell, you think you did everything right. I want to take it off the fixture and I want to stand on it. I want it to tell me my weight. All right? Can't underestimate the importance of checking your work with empirical tests anytime you can. Even a 2000G accelerometer with a modern data acquisition system can resolve 2Gs, the force of gravity. If I take an accelerometer like an Inevco 7264 with its active axis perpendicular to its mounting flange, and I zero it out, and then I turn it 180 degrees, I've got plus 1G to minus 1G, and I get a 2G check. If it says 20 Gs, I did something really wrong. This is really important. You know, when you really think about it, ultimately people's lives sort of depend on this stuff, right? And to have your data misscaled because you made a little typo or told it that it was, made a mistake in the setup is something you want to avoid at all costs. It also means that if you find out you did things wrong, you need to go back and redo work, which is expensive. So empirical tests are very important, whether it's typically the first time you wire up a transducer, you want to do an empirical test on it until you get confidence in it.